Hi, welcome to part 5 of this 6-part series about AMQP 1.0. And now we're going to go a level lower and we're going to talk about AMQP and how it manifests on the wire. And first we're going to talk about the primitive types and how they manifest on the wire. And then in the next and last part, we're going to talk about messages and frames and how they manifest on the wire, putting all those things together. So primitive types are part of the AMQP type system. AMQP has its own portable, completely language independent type system that's used for all the core AMQP elements. So when I talked about frames before and talked about parameters, all those parameters and properties are expressed in this type system. And the type system has been created specifically for fast and flexible processing and for compact representation, as you'll see. And it defines a fairly broad range of composite and primitive types for use in business applications so that no precision loss occurs. Specifically in financial applications, you'll see it has 3 decimal types, which are obviously important in financial processing. It permits descriptive references also in different type systems. So if you have a Java application on either side and you want to go and reference a particular type in that Java applications, you can go and map that into the AMQP type system fairly easily. And it also comes with its own schema language, which is fairly simple. You'll see examples of that as well. AMQP is interesting in that the type system and the wire representation can be used in one of 2 ways. It can be used as a schema in a schema-bound fashion, like Avro or Protobuf or Thrift or many of the classic RPC protocol, where you have an external schema that you kind of need to look at to know what each data element means, which prevents that you or saves you from putting metadata, descriptive metadata, that says, gives you labels for the data items that you don't have to go put them on the wire repetitively. But you can also use it completely schema-free like you would do with JSON or with message packs. So that's really up to you, and I'll also show you examples for that in this, and then also in particular in the next session. The schema language is expressed in XML. That's the only XML that actually occurring in the context of AMQP is the schema definition language, and the DTD for this is included in the AMQP core spec. And it's actually fairly simple. You define a type with a type tag, and then you give it a name, and you then give it a class. The class is either a primitive type, these are the built-in types, or a composite type, which is built from multiple elements. So that's what you see here in this example. You have a section, the properties section really of a message that's being put together from a number of fields. And so that's what's called a composite. And then you also have restrictions, and restrictions are similar to those you may know from XSD schema in XML, is that you take a base type and then you can go and further refine that base type, and that's a restriction. That's the same thing here. There's archetypes, so you can go and group types. You also have a example here. So for messages, there are types that describe the sections of the messages. And so the archetype, so the provides attribute that's here, basically says this is a section of a message, and so you can go and identify those types easier. The descriptor is also part of the type definition. That gives you a string you can identify that type with, and also a number you can identify that type with. And the number is being put together. It's a 64-bit number put together out of 2 32-bit numbers. The first 32-bit number is the IANA organization identifier, and the default for AMQP for the protocol itself is 0. And then the second part is within that namespace, kind of the number of the type. So you can use numerals, or you can use these strings as identifiers. And a composite has, and that's the special thing about the composite, has multiple fields, and the fields can themselves be of type composite. You can actually go and build hierarchies, very similar to what you can do with an XML document or what you can do with a JSON document. So the schema kind of gives you a structure around this. Composite types are always lists. That's something that we're also going to get to, what a list is and how that's being encoded. So Schemas are you're gonna see those schemas mostly in the AMQP spec, and in current practice, how AMQP is used. People tend to do more of the schema less type, but you could go and use that schema as well for your application. So here's a restricted type notion. A restricted type inherits a base source type. So we have a restriction here for the sender settle mode. I just picked schema examples from the app from the specification. This restricts a U byte, an unsigned byte, and for the sender settle mode, only 3 values are valid: 0, 1, and 2, and they also have labels. So you can now go and in your applications use those labels instead of those numbers, and then you can go and very easily translate because you have that schema definition. The schema definition here that's in AMQP is not meant to be something that immediately reflects on the wire. There's also restricted types where you say you reinterpret a type, for instance, in seconds, where there's no formal restrictions that's happening here in the type per se. It's just being affected in alias, but then in the documentation, you would say seconds has the following further constraints on top of it. And then you have, for instance, delivery annotations here is a class which really is a annotations object, an annotations structure that gets also aliased with a different type descriptor. So restricted types mostly constrain the value space or take another type and reinterpret it, kind of alias it into a different type. On the wire, data looks like this. So 2 examples. It has a constructor, and that's the first byte. So you have this constructor 0xA1, so hex A1. That is a type indicator for the string with an 8-byte length indicator expressed and the string data is expressed in UTF. That's what hex A1 stands for. And when you see hex A1, you know that there's an 8-bit length indicator following this. So that's the next one, 1E. 1E is the length of the following data, which is hello glorious messaging world. So the string is encoded using, in the minimum, 2 leading bytes, the constructor plus the length indicator, and then following that are the UTF-8 bytes. Then you have underneath a more complex type. When you have a leading constructor of 0, that means now we're following with a descriptor, and a descriptor reference is now a type definition. Reference is typically one of those schema definitions that I showed you earlier. So the descriptor is expressed here in this case as a symbol. So you have the symbol A. You have an A3 constructor that says this is a symbol with an 8-bit length indicator. Followed by the 8-bit length indicator, and that is hex 11, and then hex 11. Sorry, and then followed by the value for that symbol, and then it's example colon book colon list, and then followed, and so that's the descriptor, which now references effectively a externally defined type, and that externally defined type is a composite type. All composite types are encoded as lists. You're going to get an example of those in a moment, and then the list has a constructor code of hex 0C, and then the contents follow. So you have 2 ways of expressing these constructors. One is by just having a type indicator and then immediately following the data, or you have these more complex constructor descriptor constructs that allow you to go and effectively reference any external type with this. The fixed size data types, the primitives, all have different codes, and AMQP takes commonly used types and commonly used values and compresses them in more compact form. So the type system is kind of organized by the number of bytes that the type occupies for anything that's a fixed size thing. So the strings that we saw is a variable size thing. We're going to get to that in a second. Let's go and focus on the fixed size first. So fixed size is everything that's a number, as you can see here, or a byte sequence, or decimals, or a char, or a timestamp, or UUID. These are all fixed size elements. So the null is encoded without any data byte. So a null is hex 40 with just the constructor, and there's no data following. So the constructor itself expresses null, and null is a distinct type that applies to all other types. Boolean can only have two states, obviously. So Boolean is also expressible using two distinct constructors, and that is hex 4.1 and hex 4.2. Hex 4.1 is a Boolean with a value of true, and a hex 4.2 is a Boolean with a value of false, which means you don't need any extra data byte. You only need to have the constructor, so that's expressible in 1 byte. If you want to have a Boolean expressed in the proper way, with a constructor and a value, that's code 5 hex 5.6. A unsigned byte is a 5.0. Unsigned short is a 6.0, and that means it takes 1 byte, takes 2 bytes. And then a uint is interesting because the uint is a 4-byte type, 32-bit. So that has a code 7.0, but it has two shortcuts. One is if the value of that uint is 0, it is expressible as the constructor 4.3, and then that means that it is a uint, but the value of that uint is 0 and expressible in just the constructor byte. And if the value is smaller than 256, then it's expressible using the constructor 5.2, and then the following byte is the value of that uint. But these are still uint types values, so if you have a uint and you put it on the wire, you look at the value, and if it's 0, then you basically just put the constructor on the wire and you save those 4 bytes. So what it does, it kind of takes there's a lot of zeros we send around, and it tries to limit the number of zeros we send around and just express them in a more compact form. We often have ample space allocated for numbers that never really go up to more than 256. So it also tries to accommodate for those and just transfers them in a more compact form. As you can see, that's also true for some of the other types. So it tries to be clever about these encoding the primitives types. The variable size primitives, you already saw an example in the beginning. The string with A1, hex A1 as the constructor, then the length bit. Also, that is a clever shorthand that also exists for if you want to have a longer string, then you use a different constructor, B1, and then you have a 4-byte, a uint length indicator that you can then use for the string that then follows. So variable size primitive encodings have a 1-byte or a 4-byte preamble, and that's true for binaries and for strings and for symbols. And symbols are just specialized, separate ways of encoding a string that's specifically used for symbols, and symbols are more constrained to the permissible AMQP value space for symbols. Then there are arrays and lists and maps. So these foundational data structures, an array is expressed with a constructor of 0e, and there's also a longer form, of course, with 4 bytes, and you specify the element count, how many elements are following, and then you have the element constructor following, which then applies to every element in that sequence. So you specify the constructor once, and then all the following elements are of that type in that sequence. A list is a polymorphic array, if you will. So you go and specify a list here, C0. You see this very, very often in AMQP if you look at the type system, because all the composite types are actually expressed as lists. So you have a C0 followed by the element count, 0.3. And now that is being followed by a list of elements, each with its own constructor. So that's a polymorphic sequence. A map is a key value pair set, and the number of elements here are the total number of elements, and they're always expressed in pairs. So the number of elements for a map is always even. So here 0.4 means there's two key value pairs on the wire, and that is also polymorphic. So you have a key and a value and a key and a value expressed in that map. For composite types, the key must be a string. If you just define a map, then the key can be anything that you like. That much for the primitive types and kind of how they manifest on the wire. We're going to put that all together by investigating the composite types per se, and then also go and take a look at messages, and also how AMQP then ultimately, how an AMQP transfer manifests on the wire.